so we skipped section 15.8 because I like to cover the Jacobians first as we learn how to transform from rectangular coordinate systems to spherical coordinate systems. So this is just spherical coordinates. It's not as bad as it sounds. I think it's easier to do lots of the integrals they throw at you in spherical coordinates because spheres are so prevalent and spheres are much easier to describe in spherical coordinates. So it sort of makes a lot of sense to do this. Let's go ahead and do, for every coordinate system, there has to be a change of coordinates rule, or if you like, a transform rule, the way I was describing it in our last lesson. So let's go ahead and just begin. We'll put a point in XYZ coordinates. There's just a whole bunch of things to label in spherical coordinates. So we start with just a point in space. That's going to be this guy right here. The coordinates are X, Y, Z, obviously. Okay, we need some other, oh yeah, I guess we label the points. So that guy right there, X, Y, Z. Okay, that's rectangular. Okay, but we had like R, theta, Z in cylindrical. All right, so what's R? Better put that in. So let's see here. How about if we I'm making a mess, pardon me. Okay, so let's put an R in here, right there. And maybe a copy of it up above. Like that. And y'all know where theta lives. Here. Okay. And we know that between those two coordinate systems are transform rules, that X is our cos theta, Y is our sine theta, and of course Z is just Z, so you don't really need a rule there, but it's always good to remember that X squared plus Y squared is R squared. Okay, and then unfortunately there's another final coordinate system that uses the distance from the origin to our point of interest. And that's, that distance is the Greek version of the letter R. So it's very unfortunate that the Greek R is rho, because that looks more like a P than it does look like an R. So let's just make sure we introduce the letter here. That's pronounced R-H-O is usually how we write that. And that's just a Greek R. Okay, so it still stands for radius, right? But it's a Greek R. Okay. And so, and in cylindrical, sorry, in spherical coordinates, well, you have sort of two angles and a distance. The angles are like a latitude and a longitude. So latitude's easy, that's theta, okay? What the closest analogy to longitude is measured down from the North Pole. So if the z-axis is like your axis that the Earth rotates on, if we measured longitude down from the North Pole, we would be looking like this. Okay, and that's a phi. Some people call it phi. I think the physics teachers call it phi. And math teachers always say phi. I don't know why that is. Okay. But that's an angle. Technically, no, that's a I'm getting confused. That's a latitude. So phi is like latitude, theta is like longitude, and so latitudes aren't measured from the North Pole. They're measured up from the equator or down from the equator. So it's a little bit different from latitude and longitude. It's pretty close, just slightly different. We need some relationships here. So I think it's clear there's a relationship between R and rho, and we're going to need that. Okay, so let's block in the triangles that we need here. So I'm trying to draw the right triangle symbol there between R and the z-axis. And I think you can see that R, isn't that rho cos phi? So let's add our next coordinate system. We have rho, theta, and phi for spherical coordinates. Okay, and the first relationship I think is if you look at the sign of phi, that's going to be R over rho. So R is rho sine phi. Okay. While we're at it, z is the adjacent side, so z will be rho cos phi. Okay, and that's all pretty straightforward. Just those two facts, pretty much all you need. Those relate cylindrical. I almost want to break it up like this. So the cylindrical facts are what I just put down. So I'm going to move this down a skosh and kind of put brackets around these for cylindrical. R and Z are in that, but that takes that relates cylindrical to spherical. And then with spherical to rectangular, then you'll need an X, a Y, and a Z there. So hang on a sec here. And to be honest with you, I'm not real good at the beginning of a semester of remembering this. I do know that X is R cos theta and R is rho sine phi. So Let me make a little more space for this. Okay, so again, I'm going to erase this. X is r cos theta, okay? But r is rho sine phi. So you can do that substitution and change it to rho sine phi cos theta. Like that. Y is r sine phi, sorry, y is r sine theta. And again, r is rho sine phi. So y is going to be r, which is rho sine phi, cos sine theta, my bad. We've already figured out that that z is rho cos phi, so we can just keep that. And then the old rule for our 3D Pythagorean theorem was that x squared plus y squared plus z squared is rho squared. And that's not really an essential part of the transformation, but it's certainly important to remember. Okay, so that's a lot of rules. I'm going to put a star next to the only one that's really new, and spherical just combines the rectangular and the cylindrical rules. Okay. Yeah. Any questions? All right, so these are transform rules. We can remember that if you're going to do triple integrals, which is our goal here, and we'll do some graphing in a minute, but if we're going to do triple integrals, then we're going to need a way to transform dv into a coordinate system. So basically, we need an expression for dv. So dv, notice this won't work. You cannot do d rho, d phi, d theta. Rho would be in terms of units of length, but phi and theta are unitless because they're angles. So if you want to be technical about it, d rho, d phi, d theta is a length, not a volume. So that's not going to work. We have to remember that when there is a transformation, you have to include a Jacobian. So for dv, you'd have to have the Jacobian of the transform of x, y, and z with respect to the new coordinates here in our new coordinate system, which are rho, theta, and phi. And the order doesn't matter here for these variables. The only thing that really matters is that in the end, you'll be taking the absolute value of this. And so that's the absolute value here, and then I'll put in a d rho, d phi, d theta. And by the way, this is the normal order of integration. And I don't think you'll see us ever integrate in a different order. Okay, so just keep that in mind. First row, and then the theta and phi, usually the order is irrelevant for those two. They're the angles, and it's hard to do angles that don't have constant limits. So those are pretty straightforward. This row that you have to worry about. Okay, so the definition, let's just do our Jacobian here, partial of x, y, and z with respect to all three independent variables, rho, theta, and phi. Again, this is called a Jacobian, which is just a matrix with all the partial derivatives of all the functions. So you're going to have to do the determinant of x with respect to rho, then x with respect to phi, and then x with respect to theta. And then y rho, y phi, y theta. And z rho, z phi, and z theta. Okay. So we know how to do a cross product. This is sort of like doing a cross product. But it's called a 3x3 determinant. And I wonder if we can squeeze this in. Okay. So x with respect to rho sine phi cos phi. Okay. X with respect, sorry, y, I'm sorry, x with respect to phi is going to be rho cos phi cos theta. And then x with respect to theta would be negative rho sine phi sine theta. Okay. Any questions? It's supposed to be switched with theta. The order doesn't matter. So I use the phi, then the theta, just because that's the normal order of integration, Chris. So don't worry about that. And in the end, when you switch the order on these, it changes the sign, but we're going to take the absolute value of it. Even if it comes out negative, we're going to make it positive, because that's the rule for the Jacobian. Okay, let's keep going. Okay, so now all the derivatives of y. So y is rho sine phi sine theta. So with respect to rho is just going to be a sine phi sine theta. Oh, I don't know if you're referring to my mistake immediately above. That should be a sine phi cos theta above. So just fixing this real quick. Sine phi cos theta there. Okay. That's rho with respect, sorry, that's y with respect to rho. Now y with respect to phi will be rho cos phi sine theta. And then with respect to theta, this will be rho sine phi cos theta. Okay, those are hard. Then the z part is easy. So the derivative of z with respect to rho is just cos phi. The derivative of z with respect to phi is going to be negative rho sine phi. Okay. And then the derivative of z with respect to theta, well, it's independent of theta, so that'll be 0. Okay, any questions? Okay, and now the next part is to be a little clever. One of the things that you don't know about determinants is that you can expand on any row or column. So we've always expanded on the first row because that's where the I, J, K are in a cross product. But I like to expand along the simplest row. So the last row is the simplest. So the way this is going to play out is I'm going to write this with the cos phi first and a 2x2 determinant. Okay. Okay, and then there'll be a negative on the negative rho sine phi, so it'll be minus negative rho sine phi, like that, and then a 2x2 determinant. Okay. And then a horrible, horrible case is plus a 0. I should say the horrible part is that the part that follows the 0 is really hard, but it doesn't matter because it's going to get multiplied by 0. Okay. So those are the scalar entries on the third row. I'm going to move this over a bit because I'm going to be a little space deprived here. Okay. So when I do the cos phi, I have to block out the row and the column for the cos phi. So I'm about to kind of cross out the column and the row for the cos phi and do that 2 by 2 determinant that's up there. So I'm going to try and write small here. I start with the row cos phi cos theta. Oops. And then the negative sine phi, sorry, the negative rho sine phi sine theta. And already I'm in trouble for space. I'll deal with that later. Okay, and then the second row has the rho cos phi sine theta. And rho sine phi cos theta. Okay, so that's good. Next, for the second column where I have that row, that negative rho sine phi there, I just have to block out the middle column on this one. So I'm going to, again, give myself a little bit of space here, because this one looks like it's going to be a little bit large also. Okay, so I'm blocking out that middle column. I'm going to have a sine phi cos theta here. And then a negative rho sine phi sine theta. Okay, and then in the next row down, I have a sine phi sine theta. And then a rho sine phi cos theta. Okay. Okay, wonderful. There's still one more column. I'm gonna make space for that. Doesn't really matter what the last one is because it's gonna be 0. So I could kind of ignore it if I wanted to, but I'm gonna be good and just fill this in. So the last determinant is gonna have a sine phi cos theta. And then a rho cos phi cos theta. And then in the next row is going to be sine phi sine theta. And then a rho cos phi sine theta. Okay. So that's that. Pretty bad. I've seen worse. Okay, so we're going to be as clever as we can as we go through this. Here goes. I got the cos phi, and then inside here, I'm going to have a rho square. It's going to be a sine phi cos square theta. And then a double negative with a rho square sine phi cos phi sine square theta. So there'll be plus a double negative, rho square sine phi cos phi sine square theta. Okay. So that's the first determinant. Okay, keep going. Plus, there's a rho sine phi. And the next part, it's a rho sine square phi cos square phi. So rho, I think it's sine square phi cos square phi. Cos square theta, my bad. And I'm questioning this, so it's going to just give me a second. I'm not sure this is right. Sine square phi, sine square theta. Sine square phi, sine square theta. That's good. So there's going to be a rho sine square phi sine square theta, and I think I made a mistake. Just to the left, that should be a sine square phi, I believe. Sine square phi, sine square theta, right? Like that. And then there's a plus a 0 at the end of all that. Right now, I don't know if you noticed, but there's lots of Pythagorean stuff in here. So let's see what we can do with this first one. I see a rho square that will factor out of the first one. There's a cos phi, but also inside is a sine phi cos phi. So I think, yeah, that's good. Sine phi cos phi, yep. So we're going to factor out a sine phi cos phi with the other cos phi. So it's going to be sine phi cos square phi. Like that. And then inside, correct me if I'm wrong, but I think there's just a cos square theta plus a sine square theta. Like that. That's the first one. And on the second one, you're going to factor out a sine square phi. I think that, and a rho. So I think you're going to factor out a rho. So there will be a rho square. Factoring out a sine square phi. Is that sine cube phi? Like that. And then what's left inside is a cos square theta plus sine square theta again. Like that. Okay. Of course, these are nice, right? That's 1, and that's 1. So you end up with rho square sine phi cos square phi plus rho square sine cube phi. And it's tempting to stop, but don't, because then you've got rho square, and we're going to factor out a sine phi. Because then what's left is a cos square phi plus a sine square phi. Okay, so in the end, that's just rho square sine phi. Okay, so that's our Jacobian. We're going to pause and see if you guys have any questions about this simplification. This is going to affect all of the integrals we do in spherical. So that's never fun. And we're going to have to do one very similar to this later when we when we parameterize surface area when we compute surface integrals. So that's in the next chapter. So you'll see this in a very similar determinant later. Okay, so let me go ahead. I got to move this little guy out of the way real quick. Okay, so what we just did then is basically you've got an integral, a triple integral over a solid Q. This is in rectangular coordinates. Okay. And so you're going to have some function of x, y, and z dv. And we want to move this into spherical coordinates. So you're going to somehow represent Q in spherical coordinates. Okay. And the transform will come into play here. So it's really f of whatever x is, which I think is rho sine phi cos theta. And again, I'm just going back to these rules up here for what x, y, and z are in spherical. So rho sine phi cos theta for x, rho sine phi sine theta for y, and then z was rho cos phi. Okay, like that. But then you have to put in a Jacobian. So you would have to take the absolute value of the Jacobian of x, y, and z with respect to r theta, sorry, rho. I think I did rho, then phi, then theta in that order. And the order doesn't matter, so don't get hung up about that. Okay, so that's an absolute value. And the Jacobians are determined that we have evaluated. Okay. And the only thing I would add is a d rho, d phi, d theta. Again, this is the usual order: d rho, d phi, d theta. I do not expect that you'll need to do that in any other order than what I've put down here. I hope you don't, because I remember the last time I've done one, so it would be really weird. And the only thing I would add here is that, remember, these bars here are absolute value. Rho square sine phi is the Jacobian. Okay, and it has to be positive. So we're going to have to require that sine phi never go negative. Must be positive. And the only way we can require or demand this is that theta, or sorry, phi. I mean, basically the sign of phi has got to stay in quadrant 1 or 2 because the sign's positive everywhere there. So that is to say phi needs to be between 0 and pi. That means it's going from, remember, phi goes from the measures down from the North Pole. So that's the requirement on phi. But I mean, it'll work just fine. I mean, longitude and latitude, um, that 180-degree range from 0 to pi, that 180-degree range for latitude has never been a problem, and it won't be a problem. We restrict it to this 180-degree range, and that'll make sure that we don't have any problems with our Jacobian going negative. Okay, so all that is to say, the final form here, let's just rewrite this, but put in equals, and then the dv becomes rho square sine phi d rho d phi d theta. I'm going to move that over a bit. And that expression there, the Jacobian plus the differentials, that's dV. In spherical. Okay, so let's just kind of make this perfectly clear. So in spherical coordinates, dV has to be rho square sine phi d rho d phi d theta. Okay. And this is where my little picture is going to come into play. I don't know how in the world I'm going to get all this in. I'm going to have to make it larger, I think. Just a kind of a quick glance at a picture that I drew and that I knew I wouldn't have time to do. But this is just to sort of enhance your understanding. Down here in the XY plane, I've got this red distance to the origin. That's just R down there. But going up into space is rho. And maybe I'll do that down below. So this is rho here. Okay. And remember, phi measures down from the North Pole. So phi would be this way. Like that. And this, the angle, very difficult to get all this in here. So I'm going to chop this up even a little bit more here. Maybe just a little more. I'm just trying to make the minimal version of this picture here so that I can zoom in on it a little bit more. I'm just going to add this to the online notes. I know you're not going to be able to probably do as pretty a picture, or in the very little time that we have here. But I just want to kind of zoom in on this a little bit and do a little more labeling here. So I need to put in a d theta angle or a d phi angle here. So right here, I want to label d phi. Okay. And remember that arc length, just the old formula for arc length on a circle, it's always S equals radius times the angle. Okay. So this distance right here, and let me move things just a bit to get out of the way of what I've got here. Okay, so the little distance I'm labeling there, it's just radius times angle, but this is a circle here whose radius is rho. So this is rho d phi, right there. Now down below, I'm going to have a d theta in the xy plane. So down here is d theta, which we've talked about lots of times. There. And this bit of arc length I'll do in red here real quick. That is not as thick as I want. Hang on. Okay, so that little bit of arc length is r d theta. Again, just radius. Actually, what I need to do, forgive me for that, that's not what I want. I need to project this downward. So if you don't mind, let's see if I'm going to get myself into trouble by adding this graph. I find my vertical here. There it is, vertical. Okay, so forgive me, but I've labeled R incorrectly. So what I need for you to make sure you got is that R is just the distance to the point. What I've drawn here is rho. Okay. Okay, so I'm going to delete the stuff that's getting in the way. That's a little better. And this will fix our picture. Because our point here is XYZ, right? Maybe if I put it right there in the middle. That guy right there. And you could put it in any coordinate system. I'll just call it XYZ. And R has to be the length of this thing's shadow in the XY plane. Okay. So zooming back in down on here, I wanted to make sure I got this label right. It's this arc here that's R d theta. Right. Okay. And this is a right triangle, so I guess I could put like a right angle symbol here. Yeah, I guess. Okay. And that's already theta, and so I could measure it this way here as r d theta as well. Okay, and then this length this way would be just d rho. That's a differential in length. Okay. So note, just note from this picture, that I've got dv as this kind of this bit of volume on the graph. Okay, and I'll shade that real quick. Okay, so just mean to say that dv here would be just multiplying. The first length is d rho. The next length is rho d phi. And then the next length is r d theta. And then you go back and remind yourself that r is rho sine phi, back in the original transform rules that we were talking about. Okay, so this is rho times r, that's a rho sine phi, and then we would have a d rho, d phi, and d theta. So this is just rho squared sine phi, d rho, d phi, and d theta. So once again, this thing here is our Jacobian for the change of coordinates. Tough argument. But it sort of validates the theory of the Jacobian, that it is doing what we expect it to do. It's giving us these differential volumes with their own triple coordinates, or sorry, triple integrals, whatever it is. It just seems like the Jacobian works to find these volumes as we expect. I think I should probably try and squeeze in an integral. So, oh, just a quick question. Wouldn't rho always be equal to r? Hey, I thank you, integral of EDE. Does the correction in the picture help? Is that better? And let me make sure I did it right down previously. No, this is correct in the first graph. And how's that? Yeah, that fixes it, right? So that was just a mistake. Okay, and thanks for noticing it. Okay, anybody else? Okay, I gotta do an integral real quick. And again, this will be, I'll post this. But let's see if we can squeeze that in real quick here. Yeah, this is a good one. We got 15 minutes, so let's see if we can pull it off. So this one just says change to spherical and evaluate. And this is the kind of problem I like, just FYI. Okay. So it's an integral. It says from -2 to 2. And we're gonna probably want some space above and below this because we're gonna be putting notes down. Okay, so the first is -2 to 2. Then the next one is the negative square root of 4 minus x squared to the positive of the same square root. And then the next one, lower limit is 2 minus the square root of 4 minus x squared minus y squared to 2 plus the square root of 4 minus x squared minus y squared. Okay. And then it's inside here, you've got this x squared plus y squared plus z squared. And then these are limits for z, y, and x in that order, dz, dy, dx, like that. Okay, now the funniest thing is we actually did this today. These upper limits on z, that was a sphere we did a little bit ago. So this guy right here was z equals 2 plus square root of 4 minus x squared minus y squared. And if you work that out, I think you can make that z minus 2 is the square root of 4 minus x squared minus y squared. You square both sides and move the x squared and y squared over, and you get x squared plus y squared plus z minus 2 squared equals 4. So that's a sphere. Okay. That's the upper hemisphere. Okay. The lower limit is the lower hemisphere of the same sphere. Oops. Okay, any questions about that? We're going to need that in spherical coordinates, but let's just draw this first. So we've drawn, as I said, we've drawn this before already today. No, that's better. The radius of the sphere is 2, and the center is at 0, 0, 2. So here's a 2, and the radius is 2. So now I'll just kind of draw that out like that. So that's a length of 2 there. And then probably would be worthwhile doing its shadow down on the XY plane. So pardon me while I work on the shadow real quick. I'm really trouble, sorry. Sometimes Motability hates me. Apparently I think it hates me. There we go. Get closer. Okay. Okay, so in the XY plane, and I guess I could probably extend my x-axis to maybe make this a little better, but this top curve right here is y equals the square root of 4 minus x squared. Okay, it's a circle with the radius, the same radius as the sphere. And down below where y is negative, that's y equals the negative square root of 4 minus x squared. I've run out of space, so let me make a little more room here. Oops. So y equals the negative square root of 4 minus x squared. That's the bottom curve down there. And then x is just going to go from negative 2 to 2. So I don't know if you can see, but I'm laying out the limits on the integral. X on the back is negative 2 to positive 2. Y is a curve to a curve. And z is a surface to a surface. Okay? So the only thing I need to figure out is the formula for this surface. So let me go ahead and see if I can come up with an equation for it. The sphere, as you know, is x squared plus y squared plus z minus 2 squared equals 4. We're going to have to multiply this out. X squared plus y squared plus z squared minus 4z plus 4 equals 4. X squared plus y squared plus z squared in spherical coordinates is rho squared. There's a z here, so don't forget, and by the way, the 4's cancel, right? So you end up with rho squared equals 4z, but z is rho cos phi in spherical coordinates. That goes all the way to the transform rule in the very beginning. Rho cos phi, like that. So this becomes rho squared equals 4 rho cos phi. And on this sphere, I'm not interested in rho being 0. I want all the other points where rho is not 0. So let's just say rho can't be 0 here and divide the rho out and then say rho is 4 cos phi. So that's the equation of the sphere. With this guy here. So we're ready, I think, to put limits on our integral. I'm going to go ahead and create a sort of an arc here on my sphere going from the upper hemisphere to the bottom hemisphere. That's not looking too great. Let's see if I can pull this off a little better. That's pretty good. I'm going to patch this on here and then erase most of it. See if this works for me. Okay, that's good. Not great, but pretty good. Okay, so like I say, I'm going to erase most of that. That's all we need to do. Okay, so I like to draw like little slices going up to these things. Oh, you know what? I think I need the bottom part of that. Hang on. Yeah, one more sec. almost there. Yeah, that's good. Yeah, better. I'm sorry, I know I'm going a little long here, you guys, and I will wrap up as quickly as I can. Just one sec here. Okay. Okay, so what I wanted to do is to draw like basically a rod coming out like this. Oops, hang on. Okay. Now, inside of this sort of rod, I'm going to go ahead and create a point whose differential volume is dV. Okay. So this is my dV here. Okay. And the coordinates in in spherical coordinates is going to be rho b theta. Okay. Now, at the tip of this rod, rho is 0. On the outer edge of the rod, I'm on the sphere. So rho is the equation of the sphere for cos phi. All right. So keep all that in mind as we rewrite this integral. I'm going to just put this all down below here. Okay, so the integral, you want to go ahead and remember that the x squared plus y squared plus z squared, that's just rho squared. Okay, dz, dy, dx, that's dv. Okay, so then all you have to do for this integral is integrate rho square and then times dv, which is rho square sine phi, d rho, d phi, d theta, like that. And then we have to put limits in for rho first. And it's easy enough to see that on this little rod that I drew, and I'll shade it very carefully here in green. Okay, this little rod, my differential volume needs to go from where rho is 0 to where rho is 4 cos phi. Okay, so go ahead and put those as the limits on rho. 0 to 4 cos phi. Now, rho is done. Phi is next. Remember that phi is measured down from the North Pole. So if I drop an angle this way.
Professor?
Yep.
Down there, is that cos phi or cos theta?
Yeah. Did I do it?
There. So it's 0 to cos
theta?
theta?
Yeah, that's cos phi. Yeah, no, you're right.
It's cos phi?
Yeah, it's a phi. You're right. It's just a little typo there. Thank you. Mm-hmm. Okay, and then we're working on the limits for phi. Again, phi is measured down from the North Pole. At the North Pole here, phi is 0. So right here at the North Pole, phi is 0. So that's going to be your lower limit on this little rod that I drew. And then you're going to have to come all the way down here to where phi is going to be 90 degrees. Okay, so that's going to be pi over 2. Okay, so phi has to range from 0 to pi over 2 as it measures down from the North Pole. Okay, so those are your limits on phi, 0 to pi over 2. okay? And then finally, theta, as you know, theta, this thing that we're slicing here needs to spin all around to cover this whole circle. So that's the same theta we had in polar coordinates. So I'm sorry to rush at the end here, but theta needs to go from 0 to 2 pi. We'll just go ahead and leave it at that tonight and talk more about it on Wednesday. This will be on your exam. So if you have questions about it, I'll talk more about it on Wednesday, but bring questions. All right, I'll see you guys. Okay, so let's go ahead and evaluate this triple integral in spherical coordinates. Pretty straightforward. Integral 0 to 2 pi, integral 0 to pi over 2, integral from 0 to 4 cos phi. And we got a rho to the 4th, and a sine phi, d rho, d phi, d theta. All right. So the sine phi can actually come out one integral if you want. It's not important. It's up to you. I'll leave it. So taking the first antiderivative, you have a 1/5 rho to the 5th, where rho is going to go from 0, yuck, to 4 cos phi, which sounds just terrible, except there's a sine phi right here, which is going to take care of our differential. Sine phi, and there will be a d phi and a d theta. Any questions there? I don't know what 4 to the 5th is. 4 to the 5th is a 1024, of course. So what if we wrote it over here? So you have integral 0 to 2 pi, integral 0 to pi over 2. Again, you're going to have 1024 over 5. That's the 4 to the 5th. And cos to the 5th, yuck, of phi. And then there's a sine phi, d phi, d theta. I know the physics teachers say 5, and math teachers say phi. So sorry about that. And so again, d phi, d theta. And then I always like to do substitutions when I have stuff like this. Other people have substitutions they do in their head. But let's go ahead and say u is cos phi. Okay. And I think then that negative du is going to be sine phi d phi. And you may remember when a Jacobian comes out negative that your limits get reversed. So I'm expecting my lowered limit to actually be on the top and the upper limit to be on the bottom after the change of variables. So let's see, we're going to have a negative 1024 over 5 integral from 0 to 2 pi, and then a change of variables on the next one. I'll get the limits in a second. I think it's just a u to the 5th du. Right, and then a d theta, and then the limits. All right, when theta is 0, sorry, when phi is 0, u is cos phi, and cos of 0 is 1, okay? And at pi over 2, when phi is pi over 2, u is cosine of pi over 2 with, I'm thinking, of 0. So you see how the limits are backward on here? And whenever a Jacobian comes out negative, That's because something's been turned upside down. Okay. And here the interval got turned upside down. 1 to 0 is upside down. And so we have that negative sign. It allows us to flip it right back again. Am I okay here? So, I mean, I don't know if you want to switch it back. I guess I'll switch it back. So you, oops, my bad. So you've got 1024 over 5, integral from 0 to 2 pi, integral from 0 to 1. I've changed the sign and reversed the order on the limits. The fifth, theta. All right, so now I'm going to say 1/6 e to the 6th. From 0 to 1. That'll just be a 6th. And then that'll be theta. So I think we're getting 1024 divided by 30, and of course that'll reduce. We'll do that in the next step. And it's just an integral from 0 to 2 pi d theta. Okay. And of course that's just going to be times 2 pi. So we have 1024 over 30 times 2 pi. And I guess we'll have to think about this a little bit. So that's going to be 512 pi over 15. And assuming that's right and without mistakes, I don't see anybody complaining about mistakes. So I think that is, I'm hoping that's mistake-free. And of course, 15 has factors of 3 and 5. The only factors of 512 are factors of 2, so that's not going to reduce. And we'll just say that's done. Any questions? So that was a hard problem. How was it hard? Well, I'd say putting the limits on here were sort of ugly. Because remember, we were integrating over a circle that sat on top of the xy plane. It was not centered at the origin. And so in the equation of the, sorry, I said circle, but I meant a sphere. So the equation of the sphere was rho cos phi, which that took a little time to figure out. So I'd say, once again, that was an easy integral to evaluate compared to the setup. So we'll do a couple more integrals, but right now I wanted to just familiarize you a little more with spherical coordinates. So I've just got a couple problems where I want to sketch some regions. So remember, I'm just going to copy that picture for the original picture here for rectangular coordinates to spherical. Oops. Okay, so how about just the basic graphs? Okay, so one, what about rho equal to just a? What do you suppose that is? Anybody, you can say it out loud or type it. Remember, rho is the distance from any point, a random point. Yeah, it's just hilarious. Rho is the distance from a random point in space to the origin, And I've just set that distance to a constant. So what is the shape? That, exactly right. So this is a sphere of radius A. Of course, that's why it's called spherical coordinates, because one of the basic graphs is a sphere. And it's centered at the origin. Now, I heard somebody's voice, but I couldn't make out what was being said. And if I was to guess, I would say that was Alicia, but I don't know. Does anyone want to rephrase the question or make it something? I just didn't hear. Well, fine. I'm good. Second question. I want to set phi to a constant. So phi equals phi naught. What do you think that is? It is a cone. So we probably are going to have to draw that one. Why is it a cone? Well, just a quick little sketch, I think, will help. Maybe it's hard to see where the angle comes into play. That looks actually horrible. Okay, so I don't know what the radius is, but if you were to measure an angle, like, let me do it this way. Remember that phi is measured down from the z-axis, which I always refer to as the North Pole. So that angle right there that I marked off is phi naught. And when you measure down from the North Pole, it's sort of like a latitude, like longitude and latitude. Not quite. I mean, technically, latitude's measured up from the equator. Okay, so this is a cone. With the tip at the origin. And the angle, from the z-axis to a side is phi naught. Okay, so those are your basic graphs, what I sometimes refer to as the fundamental graphs. All right, let's do another integral. So I'm going to zoom out a bit and throw another one at you. So here I want to evaluate a triple integral over a solid that I'm calling Q. The integrand is just y squared z squared dv. Don't be tempted to think that this is meant to compute anything in particular. It could compute anything at all. Just remember, triple integrals are just computational tools. I've shown that these integrals can compute probabilities. These integrals can compute mass, center of mass, different things in statistics like variance, moments of inertia. In statistics, a moment of inertia is called the variance, as I said. But they have things called skewness and kurtosis in statistics. Those are the third and fourth moments. All of those things are computed with triple integrals. So right now, again, our job is mostly to know how to do the computations. What they apply to is going to be mostly up to your physics teachers and your engineering teachers when you're working with sort of theoretical discussions about solids or probabilities and statistics. Okay. Anyway, let's go ahead and describe Q here. So this is not meant to, I'm not implying that I'm computing anything in particular. So Q is above the cone, so above the cone, phi equals pi over 3. And below the sphere,
Professor, I think you have a frozen screen.
well, dang. I'm going to try and unfreeze it. I think that's good. Okay, so again, Q is above the cone, phi equals pi over 3, and below the sphere, rho equals 1. So those are the two fundamental shapes we were talking about just now. Okay, so let's see if we can figure this thing out. Oh, and don't forget, we're going to need all the transform rules because I see y's and z's, and those are not in spherical coordinates. So just as a reminder for the transform rules, they are probably 5 things. X is rho sine phi cos theta. Y is rho sine phi sine theta. Z is rho cos phi. There are other relationships that are on the first page of these notes. I don't think I want to be too thorough here because we're not going to need it all. We do know x squared plus y squared plus z squared is rho squared. That's just the Pythagorean theorem right there in 3D. And also that dv is rho squared sine phi d rho d phi d theta. Okay, so you need all of that to do this problem. Well, you don't need the x coordinate because I don't see any x's in this integral. Okay, so here goes. The limits look like they'll be easy because we got two fundamental shapes that are bounding the solid. So y squared z squared, so that's going to be rho sine phi sine theta. That's y squared. And then z squared is rho cos phi. Good. Okay. And just gonna do a little clean up work. This is gonna, I need more space, so. Okay. So don't forget the dv gets a rho square sine phi. D rho, d phi, and d theta. So that's actually a lot of stuff in that simple little integral. And so you kind of pay the price when you go into spherical coordinates. And there's a big payoff, and that is the solid that we're integrating through is really simple in spherical coordinates. So maybe a quick sketch of the solid would be worthwhile. So we know it's a cone. So let me get my cone going here. And I'll put in a coordinate system here. And somewhere in, I'm going to shrink this down real small. But somewhere in the midst of this, I'm going to have to squeeze a sphere in. So a little bit more here. I'm going to squeeze that down. And I want to put a sphere on top of it. I'm just drawing a sphere right now to put on that. That's not bad. I'm sure the size will be wrong. Not too bad. Pretty good. Pretty good. So I'll just try and lock that down. Maybe there. Okay, I'm going to cut that off. Okay, and maybe I'll extend my z-axis a little better. That's good. Okay, so any questions out there? You can say them out loud or just type them in. I'm going to take a second to get this finished. That's it. Anyways. I kind of want to put in my slices. So I always like to help you visualize the slices that we are cutting when we integrate. So from the North Pole, I like to draw an arc down like this and maybe give it some thickness. It's too thick. Sort of like that. Okay, and then I just pick some little patch on here. And that's going to get special treatment in a sec. Oops. Maybe I'll draw some lines down to the origin for this little piece here. Like this. That's good. Okay. Now, what you want to think about is the angles. So your feet angle is here. Okay. Maybe you could extend. I mean, if we, I'm going to do an extension of my line here. This so that we understand that that's our pi over 3 angle. Okay, so where am I going to stick that in? So I want to draw this to make sure you understand that that's pi over 3. Now, you have an end. So this is going to help get that helps get the limits on feet. Limits on rho will be at the very tip of this. The origin itself is where rho equals 0. And out at the far end of this little wand, I never know what to call this thing. I called it a rod last time, I think. So this little rod that I've created out here that I'm now coloring blue. We have to decide where it touches the surface. So at the end here, that is the upper limit for rho. So that's a sphere of radius 1, so rho is just 1 there. If I was really good, I'd add one more thing to this. Okay. And that would be the dropping down into the XY plane so I can see R. I'm going to do my best here. I don't know if I'm going to do a good job or a bad job on this. It's always so uncertain. Yeah, I'm going to try that again. Yeah, I think that's better. So that's my R. And the only reason R is relevant is that I measure theta out to it. So this is my theta. Okay, so a good picture, not bad. helps us set up limits properly. Oops. Okay, so you guys can do this. Yes, it is exactly a snow cone. Thank you, Alicia. Oh, Travis has a question. A cone or sphere cone? Can oh yeah. Um, so just real quick now, I think we've got enough here to see that on that little blue rod that I drew, at the first tip of it is the surface. It's a point, but it's also a surface. Rho equals 0. It's sort of a degenerate surface. So rho is 0 at the tip of the rod. Okay. And then rho goes up to 1. So that's surface to surface. Okay. Now, phi needs to vary so that that little rod fills up the whole slice of surface. So the rest of the surface is, I kind of don't want to screw this up, but the rest of I'm going to try to not screw it up. I'm trying, is that visible what I'm drawing? It's sort of a gray color, very pale. I'm currently shading in here. I don't know if that's going to be, yeah, that's good. Okay, so I'm just going to shade this whole slice of the snow cone in this gray color. And the idea is that rod needs to fill up this wedge-shaped slice of my snow cone. Okay. And so we have to vary phi until the space is filled. So what are the limits on phi? Again, phi cannot be measured backward. It can only be measured down from the North Pole. So somebody, what to what for phi? From where? Remember, if you go to 90, you'll go all the way down into the plane. So remember, the plane is 90 degrees down from the z-axis. And we don't want to go 90 degrees down. We want to go down pi over 3, which is 60 degrees, I think. So let's go 0 at the North Pole down to pi over 3 at the edge of the cone. Okay. Now that slice needs to be rotated all the way around to fill up the cone. So what do you want to do, guys, for theta? Yeah, so we'll go 0 to 2 pi on theta. And in the end, you computed something. And again, you're just being a calculator right now. We're not worried about what it is that you computed. Some property of that solid. Why is it not pi over 3 to pi over 2 for phi? Okay, so this, I'm going to show you right here. The blue line I drew is pi over 3. And then coming down here, that's not so good. So this line I'm drawing right now, this is pi over 2. So you would be integrating this range if you went pi over 3 to pi over 2, and that's not in the solid. So Yafe, do you see what I'm saying? You don't want this rod, this blue rod that I drew here, you don't want that to leave the solid. No, you're measuring down from the z-axis. So the z-axis is 0. Got it? So it's not, if you were doing longitude and latitude, latitude is measured up from the equator, which would be the XY plane. But we don't measure in longitude and latitude. It's almost like that. But the latitude comes down from the z-axis in math. So it sounds like you got it. We never measure up from the equator in math. Or I don't think they do in physics either. So let me just clear all this garbage out and then I'm just putting in. Okay. Well, I don't know that we're going to evaluate this whole integral because it's just more integrals. But let's clean it up at least. So we've got the integral from 0 to 2 pi of an integral from 0 to pi to 3 of the integral from 0 to 1. And altogether, I think I see a rho to the 6. Do you guys agree with that? Rho to the 6? 2, 4, 6. Yeah. And then for sine phi, I see a sine square and another sine over there. So I think it's sine cubed phi. Okay. There's cos square phi here. So that actually doesn't look too hard to do. And then what about theta? I see a sine square theta, and that is the only theta here. So we'll put in a sine square theta. And I think that's it, right? So we say d rho d phi d theta. Maybe you ought to just see, and that, and again, I think we all can do this. There's some straightforward substitutions for these trig integrals, and these are the trig integrals that you evaluated somewhere in the beginning of your methods of integration that you did in Math 181. But I think it's probably worth having you guys practice, or at least see one of these done in a computer algebra system. So just one sec. Just so you know it's out there. Maple's so good. This, I'm going to open up a new sheet and get started here. There we go. So I'm hoping, I don't know if that worked. No, there you go. Okay, so just real quick, let's key it in. So Maple's pretty good. It's got palettes for all kinds of integrals. I don't know if you can see, there's actually a triple integral palette down here. And I just clicked the wrong one. So there's a triple integral. I'll make that bigger so everybody can see it. There we go. So first 0 and then a tab and then a 2 pi. So 2 and there's a pi symbol down here. And then another tab, 0, tab, pi over 3, tab, 0, tab, 1. So those are my limits. Now this is the ugly part. I've got a row. I believe there's a Greek alphabet down here. So I'll put in a row to the 6th. And then a sign. Okay, I think it's like sign. Of phi. There's a phi right there. And then you should do the to the 3rd outside of the sign and not inside. And then there's a cos of the same variable phi, and that should be squared outside of the parentheses like that. Okay. And then a sine square theta. Like that. And now I can say d rho right there, d phi there, and theta there, and just hit enter. And that's a beautiful thing right there. So I'll just put in the answer here. 47 pi over 3360. Okay, and the trick here is setting these up. Oh, Chris, this is Maple. And if you're interested in Maple, they have student licenses. Let me know, and I might be able to get you a discount. We don't have, Mount SAC doesn't have any investment in Maple or anything like that. It's a terrific program. Okay. Any of you guys that are interested, I think I can get student discounts on the student version. It's still going to be like $75, but it's an amazing program. Okay, let me go back to the iPad. I think that's all we're going to do with this. Okay, so any questions about all that? Okay, so see what you can do with your cylindrical coordinates. We'll be taking questions during office hours if you want to ask. Don't forget, I got an office hour on Friday at 11:40, and also on Monday, there's an office hour from 11 to 12:30 in the morning. So you can ask me then. Don't forget your test is Monday. Okay, and it will include spherical coordinates.